Welcome to our lecture online. Here's our next example with a ladder problem. There's whole kinds of different scenarios we could run into. Here's scenario number 4. We have friction both at the bottom and at the top, but in this case at the top the ladder is resting right at the corner of that wall right there, which means that the normal force is perpendicular to the ladder at that point, and the friction force will be parallel to the ladder at that point because the friction force must be perpendicular to the normal force. Again, we're looking for the coefficient of static friction that will prevent the ladder from slipping. We're going to do the same thing we did in the previous video. We're going to use the sum of all the force in the x direction to try find a relationship between the normal force at A, the normal force at B, and the coefficient of static friction. So we're going to sum up all the forces in the x direction. So first of all, we have this in the positive direction. So that would be, they add up to 0. So we have the normal force at A times the coefficient of friction. And then we have the normal force at B, but we want the component that's horizontal. So what we need to do is, if this is the hypotenuse, we have to multiply times the cosine of this angle theta to get this component of n sub b, and it's in the negative direction, so that would be minus n sub b times the cosine of theta. And then we need the component in the horizontal direction for the friction force, and that would be this angle right here, theta. That means we need to look for the opposite side of that angle, and that would be plus, because it's pointing to the right, the friction force, which is n sub b times mu sub s, times the sine of theta, and all this adds up to 0. So what we want to do with this equation is exactly the same as we did in the previous video. We want to relate the ratio of n sub a and n sub b to mu sub s. To do that, we're going to move this over to the other side. So on the left side we get n sub b times the cosine of theta minus n sub b times mu sub s times the sine of theta. And on the right side, we have n sub a times mu sub s. And then if I factor out an n sub b, I can do this. I can factor out an n sub b. So n sub b times cosine of theta minus mu sub s sine of theta is equal to n sub a times mu sub s. And then if I move n sub a to the left side here and move this to the right side, I can now write that n sub b divided by n sub a is equal to mu sub s divided by the cosine of theta minus mu sub s times the sine of theta. Next, what we need to do is take the moment about point C so we can eliminate the weight of the ladder, since we don't know the weight of the ladder. So we're going to sum up all the moments about C. Sum the moments about point C, that adds up to 0. So we have n sub a, which is gives you a moment in a clockwise direction. That's minus n sub a times the distance. That would be from the line of action of force to the pivot point. That would be 2 feet. And then we have plus n sub a mu sub s, plus n sub a mu sub s times this distance right here, which is half of 9.6, which is 4.8. And then we have n sub b, which gives us a counterclockwise moment, so plus n sub b times this distance, because it's perpendicular to the ladder, which is half of 10.4. That would be 5.2. And then we don't have to worry about friction b because it's along the line of the ladder that line of action goes right through the pivot point. So we don't need to worry about that. So now we have this equation set equal to 0, and somehow we have to have an n sub b divided by n sub a so we can eliminate that ratio. And I think we know what to do here. Let's move this over to the other side. And, well, we could also divide everything by 2. So this by 2 becomes 1, this becomes 2.4, and this becomes 2.6. And then moving this over to the left side, we get n sub a minus 2.4 n sub a times mu sub s equals 2.6 n sub b. Then we factor out n sub a on the left side. So n sub a times 1 minus 2.4 mu sub s equals n sub b. And then finally we can come up with that ratio. Oh, I forgot my 2.6, didn't I? 2.6 n sub b, there we go. And n sub b divided by n sub a. So we move n sub a over here. We get 1 minus 2.4 mu sub s is equal to 2.6 n sub b divided by n sub a. And then get rid of the 2.6, put over here. Now we have that ratio here. We have 1 minus 2.4 mu sub s divided by 2.6 equals that ratio, which can now be replaced by this. And to simplify things, let's say that this is mu sub s divided by the cosine. So I have the angles here. Take the cosine of that angle. That would be 0.923. 0.923 minus mu sub s times the sine of that angle. So 22.62, take the sine, gives me times 0.3846. There we go. So that is equal to the ratio of n sub a, n sub b divided by n sub a. Like so, which can then be placed in the equation over here. So now we have 1 minus 2.4 mu sub s divided by 2.6 is equal to, we have mu sub s divided by 0.923 minus 0.3846 mu sub s. All right. Now we have to turn that into a quadratic equation. So we cross multiply and we get 0.923 minus 2.4 times that. 2.4 times 0.923 equals, that would be minus 2.215 mu sub s minus 0.3846 mu sub s. And then this times this gives us plus 2.4 times 0.3846. That gives us plus 0.923 mu sub s squared. And multiply that times that equals 2.6 mu sub s. All right, it's becoming more and more like a quadratic equation. Now we just need to place everything over to one side. And since I need some more room, let me go over here and see what we get. On the left side, we get 0.923 mu sub s squared. Then if I bring this across over here, that becomes a minus 2.6. Added to this, that's minus 4.815, minus 4.815 mu sub s. And I have a positive 0. Oh, I forgot one more thing. I forgot this one right here. Got to be careful. There's 3 mu sub s's I need to combine. So let me get my calculator. So we have 2.6, that becomes minus 2.215, and minus 0.3846 equals, and this becomes a minus 5. Let's call it 20 mu sub s. And then I have one constant over here, which is plus 0.923, and that equals 0. So here is my quadratic equation, which I can now solve for mu sub s. All right. The equation then becomes mu sub s is equal to negative b, which is a positive 5.2, plus or minus the square root of, that would be 5.2 squared minus 4 times a times c, which I can simply just square that and divide the whole thing by 2 times 0.923. Good thing we have calculators. All right, so 5.2 squared, that would be minus the quantity 0.923 squared times 4 equals, take the square root of that, and that gives us 5.2 plus or minus 4.86 divided by 2 times 0.923. I think the best choice here is to subtract 4.86 from 5.2, n divide by 2, n divide by 0.923, and we get the static coefficient of friction required to keep the ladder from sliding is 0.1835, something in that neighborhood. And again, you can see compared to the last problem, we had mu sub s equals 0.2, but since it's now resting just at the corner, the static friction required is just slightly less than we had on the previous example. Again, most of this is algebra, but once you set up the problem, once you find the relationship between the normal forces in terms of mu, using the sum of the force in the x direction add up to 0, and setting up the moment about the midpoint of the ladder so we can eliminate the weight of the ladder, and then somehow rearranging this equation until you have that ratio of n sub b over n sub a that you can replace this equation with. And at that point, it's all quadratic equation to solve for mu sub s. And that's how it's done.